us go to another example which is PBCA. This is because this is one of the, see, I have taken all the common crystal systems which you come across, particularly chemists come across, and also in pharma industry. You will come across only lower symmetry systems because you are dealing mostly with organic compounds, and the pharmaceutical compounds have all these functionalities which make the molecules very flexible, and so the crystal systems into which they go into a lower symmetry space groups. And therefore, I have considered the monoclinic, the triclinic, monoclinic and orthorhombic systems. So, among these systems I have considered only the most commonly occurring systems. So, we discussed P21 upon C as a most commonly occurring centrosymmetric monoclinic system. The non-centrosymmetric 2-1, 2-1, 2-1 in the orthorhombic case is very often occurring, and PBCA is the one which is its counterpart as far as center of symmetry involvement is concerned. So, it is actually P21 by B, 21 by C and 21 by A. That means it is a B glide perpendicular to the A axis, C glide perpendicular to the B axis, A glide perpendicular to the C axis. So, this in this particular system, of course, we have studied the way in which the symmetry elements come up. Additional symmetry elements show up which are not really indicated here, they will also show up, and as a consequence we get 8 equivalent points in the unit cell. So, those equivalent points are the general points, and therefore, there are 8 equivalent points which represents the multiplicity of this site XYZ, and then the symmetry associated with the site is 1. This particular space group has 2 possible special positions, again associated with 1 bar. As you see, it is a consequence of the value becoming half or 0 depending upon the generation of the symmetry associated with these 8 equivalent points. So, what are the conditions? The general conditions are 0 KL K even, HOL L even and HKO H even. So, what does this represent? This represents B, C and A glides, and the association of these 3 with respect to the A, B, C makes it PBCA, but the systematic absences are with respect to A, B and C all 3 together. Now, the special reflections, axial reflections H00 and 0K0, 00L will also develop because it is the system is 2-1 by A, 2-1 by B, 2-1 by C, the full system, because the point group symmetry associated with this unit cell is MMM, 2 by M, 2 by M, 2 by M, and so these are the general systematic absences. Once it occupies the special position, the center of symmetry in PBCA, it takes up 2 possible Wyckoff positions, A and B, C being the general Wyckoff position, and this Wyckoff position will generate 4 equivalent points 0, 0, half. So, you see that the conditions look as though what? It looks as though they are F centered lattices. You remember the conditions for F centered? So, this looks as though they are F centered lattices. So, what you have to do is never look at this special absences, look at only the general absences to determine the space group. So, these are occurring mainly because of the way in which the atoms are positioned inside the lattice. So, suppose you take a PBCA lattice and put these equivalent points, you will see automatically the generation of the face centered symmetry, because you have a 0, 0, 0, you have a 0 half half, you have a half half 0, and you also have a half 0 half. You see here these 4 positions essentially tell you it is a face centered lattice. The way the atoms are located, this is what we did in the case of zinc sulphide when we took the example of zinc sulphide in the earlier classes, and we found that it belongs to C2 by C. If you want, you can go back to that example. You will see that the presence of the face centering in PBCA comes because the atoms are positioned in such a way they mimic a face centered lattice. Since this is now face centered lattice, you will get face centered absences in the general reflections, and so it is not an F centered lattice, it is still a PBCA with special position which is associated with the Wyckoff A, and that is how we have to interpret the symmetry indications shown in the international tables for crystallography. Now you see the importance of analyzing the equivalent points, their presences and absences, and then identifying the space group to the extent possible. So again and again I have been stressing that if there is an error here, you will never get the structure determined, and if the machine also makes a error, which is quite possible, then also you will never get the structure. So this point has to be borne in mind, and what you have learned so far in this particular course is very crucial for this. See, once you have these unusual systematic absences coming up, since you have not done the structure, you see these are coming up because now you know where the atoms are sitting, right, in this special position. It does not tell you the structure information. You do not have still x, y, z, that is what you have to determine. But before you even determine the x, y, z, you know in this particular case the atoms have to sit in special conditions and follow this systematic absence. So it is an advantage. So this is the advantage of putting the atoms and molecules inside the unit cell and keep the symmetry information, which is very crucial for determining the space group. I think I have stressed enough on the space groups until now, and we will wind up the discussion on the space groups at this moment. So we will now look into the other properties of the structure factors. So we have actually here, when we are discussing the systematic absences, we are actually looking at the presence or absence of structure factors, right, because it is f of HKL we are looking into. So the f of HKL has a special property that is known as the Friedel's law. So the Friedel's law is a very special property which makes the diffraction always centrosymmetric. So your crystal system may be non-centrosymmetric. Let us say 2 1 2 1 2 1, P 2 1 2 1 2 1 is your space group. Then it has to be a non-centrosymmetric system. But when you do the diffraction and when you do the scattering experiment and get the diffraction done, you will get a symmetry, center of symmetry associated with your HKL distribution. That means for every f of HKL you have a corresponding minus of h, f of minus h minus k minus l, and this is known as the Friedel's law. The disadvantage with the Friedel's law is the fact that you cannot identify the non-centrosymmetric feature associated with your space group, or for that matter the symmetry that is associated with your crystal system, because the data always is centrosymmetric. So for the X-ray diffraction, therefore when you do the X-ray diffraction experiment, your number of point groups will reduce from 32. In fact, it will become only 11, and these 11 are known as the Laue group. So a diffraction experiment therefore will not directly give you the 32 point groups. This is a revelation at this moment, but we will have to live with it because X-ray diffraction is centrosymmetric. Why is it so? Intensity of X-ray reflection is the product of relevant structure factor and its complex conjugate. Mathematically, I of HKL is expressed as f of HKL times f star of HKL, and I have written down below what is f of HKL and what is f of HKL star. So if you look at f of HKL, it is sum over 1 to n of the cosine term plus I times sum over 1 to n of the sine term. This is the general expression for the structure factor, because now you know that we are not expressing in terms of the exponential, we are expanding it as cosine theta plus I sine theta. So this therefore is f of HKL. The corresponding complex conjugate f of HKL star can be written as I equals 1 to n of the cosine part minus I times the sine part. Then if you take f of HKL and f star of HKL and take their product, you will end up with I, and therefore when you take the square root of I of HKL, what you get is not f of HKL directly, you get the f of HKL modulus. Because of the fact that there is a phase information that is contained in this one, we will have only the modulus coming in, the phase does not come up when you take the square root of the intensity. And therefore this expression can be considered like this, since cosine of minus theta is equal to cos theta, and sine of minus theta is minus of sine theta. If you substitute, you get f of HKL square star as equal to sum over 1 to n f of n cosine 2 pi minus of hxn minus of kyn minus of lzn. That means we are taken minus hxn minus yn minus zn as the possible coordinates of the atom instead of xn, yn, zn. So, that means to say we are now considering the centrosymmetric equivalent. So, for every x, y, z there is a x bar, y bar, z bar in a centrosymmetric system. So, here we are bringing that concept into the positioning of the f star of HKL as fn of cosine 2 pi minus hx minus ky minus lz plus I times sum over 1 to n of fn sine 2 pi minus hx minus ky minus zn. So, what does this represent? This represents f h bar k bar l bar. So, f of HKL star is equal to f of h bar k bar l bar, and you see that f of HKL can be shown equal to f of h bar k bar l bar star. So, the complex conjugates are related to each other by this mathematical fashion. So, f of HKL star is f of h bar k bar l bar and f of HKL is f of h bar k bar l bar star. So, we can rewrite this expression for f of HKL and then you will see this equivalence coming up. Therefore, because of this feature of the complex conjugate nature of f of HKL, you will get I of HKL is equal to f of HKL times f of HKL star, and that is equal to f of the h bar k bar l bar, because f of HKL is equal to h bar k bar l bar star from this expression, and from the other expression you write f of h bar k bar l bar. And what does this represent? If f of I of HKL is f HKL f star of HKL, then f of HKL bar all of bar times f of h bar k bar l bar star. This should represent I of h bar k bar l bar. That means I of HKL is equal to I of h bar k bar l bar. So, therefore, what we see is that the intensity that you measure is always has a centrosymmetric component. So, this is where we calculated the possible number of reflections by making use of that formula which told us the volume of the limiting sphere and the volume of the reciprocal lattice, and using that we calculated the number of reflections that are possible, and that turned out to be for a given wavelength lambda, because it depends on lambda cube 1 over lambda cube, and we found out that in the case of molybdenum radiation it is 1,42,000 something. But you see that half of it is redundant, because whatever you have measured as I of HKL, the other half of I of h bar k bar l bar is identical. So, you actually measured the reflection twice, and as we will see later, the symmetry associated with the system will also make some other equivalences, and because of the fact that there are some other equivalences with high intensities, the number of reflections you collect start to reduce. The I of HKL equals I of h bar k bar l bar is a universal relationship, and it is always valid unless under special circumstances. So, for all practical purposes this is a valid law, and therefore, we end up with 11 Laue classes. So, the 11 Laue classes can be followed into the 7 crystal systems and the corresponding point groups. So, the triclinic has 1 and 1 bar, the Laue group will have only 1 bar. So, the 2 systems that are associated, 2 point groups will be essentially 1 point group as far as diffraction is concerned. Similarly, in the case of the monoclinic system, 2 by m is the only possibility, MMM is the only possibility for orthorhombic, and so on. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These are the 11 Laue classes. So, for a diffraction experiment, therefore, there are only 11 point groups symmetry. And so, how do we now find out the realistic point groups? The determination of the realistic point groups will come in later, but in the do a diffraction experiment, you will get only the Laue symmetry. Now, just in the passing, I will also tell you what happens in case the Friedel's law is not valid. Under what circumstances Friedel's law validity goes off. One of the things which we will notice in a practical experiment is that when we actually measure the intensity of HKL and measure the intensity of H bar, K bar, L bar using a detector, the counts which we get on the detector will not be exactly equal. They will be nearly equal. If I of HKL is very strong, I of H bar, K bar, L bar will also be very strong. But we do not expect the numbers to be, let us say, 10,000 and 10,000. So, there will be a difference between these two, but that this difference will be minimal. The difference is due to the fact that we have a crystal. So, X-rays are coming from air or a rarer medium, and they are going to the crystal, which is a denser medium, and then they are scattering. So, even though we treat this as essentially a reflection, they are going through a denser to a rarer to a denser to a rarer medium before they are measured, and therefore, there will be differences depending upon where exactly in the crystal HKL is located and where exactly in the crystal your H bar, K bar, L bar is located with respect to the defined origin, and therefore, the intensities will be slightly different from each other, but Friedel's law will still be validated. So, when you put this data on an absolute scale, you will see that they are nearly equal. But when you actually do this exercise with a compound where you have a very heavy element and it is going into a non-centrosymmetric system, it is possible that the system which now is generated may show I of HKL as not equal to I of H bar, K bar, L bar. So, what was in my example 10,000, it may become 4,600. There is a huge difference between these two. It cannot be mainly due to the absorption or the size of the crystal, it is due to some other effect. That some other effect is known as anomalous dispersion. And this anomalous dispersion is in fact a very useful tool. This was discovered by a person called Byfoot. So, it goes according to his name. Let me write it somewhere. Very interesting spelling, pronounced as Byfoot. So, you can say Bijwayot if you want, that is what most of us spell it, but it is pronounced Byfoot. So, this gentleman found out that the differences is due to something very interesting, and that is the phenomena of anomalous dispersion. So, what happens in anomalous dispersion? I do not think this is within the core purview of our course. So, I will just describe verbally for a couple of minutes what this process is all about. The process is that when X-rays fall on the given element by the intensity which is falling on the element, it is possible that the energy that is associated with the X-rays, incoming X-rays, is sufficient enough to knock out the K shell electrons. So, there are 2 electrons in the K shell for any element. So, the 2 electrons go away, and the immediate action will be that to keep the stability of the atom. The immediate action is that there is a transition from the next, which is the L shell, to the K shell. So, the transition from the L shell to the K shell is accompanied by emission of radiation, and that radiation is the so called characteristic radiation, which will be a very sharp X radiation, which is what we use in our diffraction condition, which is what we use for input for copper radiation or molybdenum radiation and so on. We pick up that characteristic radiation. We have discussed this in an earlier class as well. So, what happens therefore is that this particular wavelength has a certain, of course, when we say wavelength, it has a frequency associated with it. And now, if there is an atom which has a frequency or that difference between the K and L shell is about the same as that of the wavelength which is coming in, if the distance, then it does not know whether to stay there or go out, because the frequency matches. And because the frequency matches, these electrons now they do not know what to do, they reach relativistic speeds. As a result, whatever scatters from the atom becomes anomalous. and this anomalous behavior is the one which causes the change in the observation of I of h bar k bar L bar being different from I of h k. People have estimated the possible effects, and we will be discussing it at a later time if time permits, because this is out of the purview of this particular course. But what is important is that by observing these differences, we can actually identify the absolute configuration of a given molecule in the crystal. So, when we discuss the structure determination protocol and the absolute configuration, at that particular time we will spend a little extra time to see how these bifoot differences, as they are called, the difference between HKL, I of HKL and I of H bar K bar L bar are referred to as the bifoot differences. The presence of the bifoot differences can be utilized to determine the structure of the absolute structure of an organic molecule. In fact, it can also be used to determine the structures of large proteins, again due to this anomalous dispersion effect, because what the net effect will be is, you can guess, is the fact that your scattering factor f versus sin theta by lambda does not know how to behave, because only when the atoms go out of the K shell and generate that wavelength, you will have this f versus sin theta behavior associated with the atom. But now the atom is also vibrating with the same frequency. So, the problem is now it will therefore completely absorb the radiation which is coming in and let out something else, and that something else is what we have measured as the intensity, and therefore that information can be used. So, the scattering factors get modified. The scattering factors which is real so far will also become imaginary. So, we will have a component of f, we will have a component of f. So, what was f, which was a real quantity, now becomes f naught plus I delta f, a real component on the Argand diagram, plus I, sorry, there is no I here, delta f prime, that is the real component, and then I delta f double prime. We will have a slide illustrating this detail and how to do the absolute configuration from anomalous dispersion when we discuss the structure determination aspect. So, at this moment we end up with 11 Laue classes. So, in a nutshell, we have a data, we have a crystal, we are sent in the X-ray beam, and we now want to collect the data. And when we collect the data, we look at the intensities, and these intensities now can be analyzed with respect to systematic absences, and the systematic absences will tell us the space group. The diffraction apart from that is also now essentially obeying the Friedel's law in most of the cases in general, and because of the fact that it obeys the Friedel's law, the number of point group symmetries will reduce, because we will get only the centrosymmetric information in an X-ray diffraction pattern. So, we will get therefore the 11 Laue classes. So, the 11 Laue classes are essentially shown here, and the scattering therefore is essentially this. So, the diffraction pattern, your HKL reflections which you get will be always with respect to the center of symmetry. In addition, the fact that we have higher symmetry elements in monoclinic, orthorhombic, trigonal, etc., as we go higher and higher in symmetry. For example, because of the fact that B axis is unique and we have a 2 by m symmetry in the data, the HKL reflections, will be equal to H bar K bar L bar, and also if you have a H K bar L reflection, it will also be equal to HKL. Therefore, there will be other equivalences which will develop, and therefore, the symmetry that is contained inside the data set will also sort of tell us to which crystal system the data will correspond to. and that is something which we will see in a next slide in the coming class. So, essentially therefore, we have covered the various aspects of space groups. The reason why I am repeating it again and again is because this is the crucial step and we should not miss any of these points, and therefore, let me go through it once. Suppose you consider an A glide, we have these systematic absences when L is equal to 0. We will end up with this list where we have the conditions to be satisfied for a glide plane parallel to 1 0 0, glide plane parallel to 0 1 0, these are the conditions to be followed, glide plane parallel to 1 1 0, these are these systematic presences. Similarly, in case we have the screws axis symmetry, we see these conditions coming up. And then we have analyzed this with respect to individual space groups, the conditions which come up as general reflections take the precedence over the conditions which come from special reflections. In this particular example of C2, there is no such worry, but when we go to something like P2 upon C, you see as though this is a glide plane additional to the existing glide plane. It is not that way to be interpreted. In fact, this is a HKL, so it looks as though it is a centered lattice. So, this gives you the information that it is a centered lattice, and that is because if you look at now the positions of the atoms in the unit cell, the positions of the atoms in the unit cell mimic a centered lattice. They are still in P2 upon C. So, to determine the space group uniquely, one has to refer to the general systematic absences. And suppose you have recorded a data and then only these absences come in. This is a point which we should now discuss. Suppose I record a data and that data gives me only these conditions. What is your conclusion? Your conclusion is very complicated now because your crystal system is P2 upon C. You determine ABC alpha beta gamma by the distribution of the DHKL values. You found out the ABC alpha beta gamma. We are going to find out in the next set of classes exactly the methodology which is used, because I thought that instead of describing it at this particular position, it is better we describe it with respect to the experiment you perform, because now the logistics will be from here on to go to the actual experiment which we perform. So, we will take the crystal, we will take the sample, grow the crystal, examine the crystal, put it on the machine, and then the machine collects the data. So, what I thought would be that with respect to the machine, we will now see how things move, because that is what you are practically going to use in the rest of your crystallographic adventure. You are not going to use any of these things which we have learnt, but whatever we have learnt is going to be extraordinarily useful when we want to do the experiments. Otherwise, we will do the experiment blindly and it can always lead to the wrong direction. So, as I mentioned earlier in one of the classes, that Jack Dunitz says that chemist makes the compound and puts it in a dark room, he does not know where is what, and the crystallographer comes into the room and switches the light on, and then you will see where is what, and that is how it is. And therefore, what you have to therefore do is to see that we get an idea of the way in which the systematic absences come up. So, coming back to the question which I have asked, which I have posed, I get a indication that this system is P2 upon C, but I get systematic absences corresponding to a centered lattice. So, what do I conclude? Do I conclude that mine is P2 by C is wrong and say this is now a centered monoclinic system, which is quite possible to have? What is your conclusion? The conclusion will be that we have to look at always the general reflections, but then the general reflections are also not shown, only these are shown. So, what is the conclusion? The conclusion is that if we have these special conditions that are coming up, these special conditions that are coming up is because of the atoms being in very, very special positions. It is not coming up because the unit cell is this. This is where the confusion comes. See, for example, if there is a compound which is crystallizing with all these atoms in these positions, let us say any of these positions. Let us say the molecules are associated with 0 0 0 0 half 0. Now what is very interesting is only if and only if the atom is sitting at these positions, you will have this, if it is an atom. If it is a molecule, only the molecule's center of symmetry will sit there, and the center of symmetry of the molecule need not have any atom. Okay. The molecule, there may be one atom in the molecule which may sit. For example, it could be a organometallic compound. The metal atom may sit at this position, but the fact that the other atoms are sitting in other general positions will not give you only these. These will come only if the atoms are in these positions, but we are dealing with molecules, we are dealing with compounds, we are dealing with complexes. So in such situations we will straight away get these. So only if there is an atom which crystallizes in the space group P21 upon C with which is sitting at 0 0 0, you will get this systematic absence. So if there is a organometallic compound for which you have collected the data and you try to solve the structure by P21 upon C, you will have difficulties. You will have difficulties because the phase which you are going to determine is dominated by the heavy atom position, and therefore then you will have some difficulties to overcome, and that is something which is very special to very few compounds. So we will not discuss that, that is beyond the purview of this particular course. However, you should remember that if the conditions are such that we do get atoms that are present in these positions, you will also have this indicated in the general reflections. So the same logic we extended to 212121 and in particular PBCA, where we get an absence equivalent of a F-centered lattice. And therefore we see that we have the following information: we have the space group information, we have the Friedel's law information, we have the intensity data that is collected, and we know that the diffraction is essentially belonging to 11 Laue classes. So what we do next? What we do next is we have now the entire grammar book written up. We have all the necessary information which is required to do a diffraction experiment. So it is at this stage we can go ahead and do the diffraction experiment, which we will do. So the next step would be to do the diffraction experiment, grow the crystal to start with, check the crystal for diffraction quality, put it on the machine, and then get the diffraction data. And once we have the diffraction data collected using a counter of different kinds, we can use CCD, various kinds of machines, to find out the intensity that comes in the form of a reciprocal lattice point reflection. And that particular intensities and the position of HKL will allow us to determine the geometry and also the structure of the given material. So that will be the next step. So we now have reached a stage which is the milestone of understanding the symmetry and structure in the solid state. The next one is therefore where do we apply? Obviously we apply to determine the structures. So to determine the structures, we now have a situation where we have to now get to the compound. So get to the chemistry of it, get to the actual experiment. The idea of this course is not to describe the experiment in detail, even though we need the experimental results to again go and understand the symmetry and structure in the solid state. So we will get some basics of the experiments. We will also find out that the major issue, as we have always been discussing, is the so called phase problem. The experiment is giving us only the magnitude of the structure factor, and we need the structure factor to do the Fourier transform to get the electron density. So that means we need the phase information. We also know very in a passing discussion that if we use intensities of HKL, the Fourier transform of that will give us what is known as a Patterson function, which essentially gives us a vector map of the distance between each atom to the other. So we get an interatomic vector display on the 3-dimensional projection, and that will have some special properties obviously which we have to examine. So the logic therefore is now we will go find out how do we collect the data and so on, accumulate the data, analyze the data, put the data on an absolute scale, because whether you collect the data in Bangalore or Timbuktu or somewhere in synchrotron radiation, the crystal or the material is still the same, and therefore you should get the structure of the material You don't care what radiation you are using, what diffractometer you are using, what kind of scaling is there in that, and so on. What you want is to put the whole thing on a common scale, which is the absolute scale. The absolute scale comes from the fact that we can, you see, the scattering is done by the electron density, right, inside the crystal. So it does not matter where the electron density is. What matters is the total electron density. The total electron density does all the scattering experiment. So based on that idea, the total number of electrons matter. So if you now consider the total number of electrons in the crystal system, that is the one with respect to which we do the scaling, and that is something which we will consider in the next class.